So in this section, in this video, we're going to talk about the matched pairs test, which is also one of our t-tests. But this one's different because this one we're going to often use when we are doing something utilizing pre and post test. So, and it also gets called the mean difference test. So you may see that outside of your literature. Now, what is a matched pairs test? So a matched pairs test is a statistical test where we compare the individual data values in two samples on a pairwise basis. So the matched pairs is also called a mean difference test. So one of the things is that we have to make sure that the data in both of our samples are paired up, right? That one element in each sample corresponds to another element in the other sample. All right, so that pairwise matching is one of the key ways that we can tell that we're doing a matched pairs test. All right, so let's talk about a little bit about the difference between the matched pairs and say something like a t-test. So one, in a matched pairs test, the samples are dependent. All right, that means that in one sample, there's a member whose value of the variable in question is dependent upon the value of the member in the second sample. So if we think about it in a pre and post test, what that means is that the person in the first collection, that's their pre-score, and in the post collection, it is their post score. And so hence, the two samples are the pre-sample and the post-sample, and they're always paired up based upon the individual that's the same in both samples. Or we might actually go in and we might do something called propensity matching, which is where we construct a person in one sample that is basically identical to the other person in the other sample, okay? And that allows us to actually eliminate any kind of confounding variables. Versus if the two samples are independent, and we talked about this a bit in the two-sample t-test, they do not have any relationship other than being part of the same experiment or observational study. That is that they are two different populations. So this is the dependent samples, they're the matched pairs, and the independent samples, that's the two-sample t. So oftentimes in like a randomized clinical trial, each individual is then randomly assigned to a grouping in the experiment, and that actually like a treatment, no treatment group. And so that consequently is the two samples. So there's no relationship between the two samples other than, like we said, being in the same experiment. All right. If we're doing a matched pairs, our null and alternative hypothesis are these. One, H naught, our null hypothesis is that mu d equals A. Most often this is 0. If we say that mu d equals 0, that means that there's going to be no difference pre and post. So there's no difference pre and post, okay? On the other hand, if we use our alternative says there is a difference pre and post, right? Either we don't know the difference, or we hypothesize that it's going to be improved or greater pre to post, or that it's going to decrease pre to post. If, like, say, for example, we're looking at cholesterol and we want to see, does cholesterol decrease, right? We might want to see that the mean difference goes down, all right? And then if we write that, the mean difference between the pairs and the two samples is not 0, okay, or is not A, whatever A is. All right, so when we think about this, my null hypothesis is that there is no difference, that there's no effect of my treatment. Okay, so like let's take a look at an example. Will the introduction of assisted yoga to persons who require living assistance improve independence? And then we'll test this significance with a significance of 0.01 in this case. So our explanatory variables are assisted yoga, walking as an exercise group, and no exercise treatment. And what we're going to look at is we're going to do each one of these groups with pre and post. Before treatment and after treatment, okay? And then we'll use a Bartle score, okay, for our ways of determining whether or not they have improved independence. So each individual, now we look at the experimental design to tell us that in fact we're going to use this pre and post, is randomly assigned to one of the treatment groups, and their Bartle score is assessed before beginning of the experiment. After 6 weeks of the experiment, Bartle scores are assessed again, right? So we've got that before and after. Sample 1 will be the before group, and sample 2 will be the after. Okay? And what we're looking to do is, will introduction of yoga improve our Bartle score? All right. So, in our example, we would assume that in the absence of any treatment that the individuals should not improve at all. Why should I expect any kind of improvement, right? Okay, so that's our mu d is equal to 0. The average difference, on the other hand, if our treatment of assisted yoga is effective, then we might actually see that we get a change in our mean difference, and that it would in fact increase. Okay. However, it's possible that we might have maturation effects, so we'll want a no treatment group. We want to see what would happen under the no treatment, right? So we want to deal, sometimes we want to deal with confounding variables. Okay. Also, we might assume that the exercise, that just simple any exercise will improve Bartle score, and so consequently, that's why we're going to add the walking group, right? What if it's just exercise at all and it's not actually assisted yoga that makes a difference? All right, now requirements for the test. First, the members of each sample are paired, either via similarities in variables under question or because the members of the samples are the same subjects. And so that's our pre and post. Then we have some assumptions of normality. They're very similar to the two-sample t-test. One, the populations for the variables in question are normally distributed. Okay. Two, if the populations are not normally distributed and we have n between 12 and 40, the samples are roughly symmetric and unimodal, or n is greater than or equal to 40. Okay. So let's take a look at the histograms just real quick and see if we have roughly normal distributions. Okay. So I'm going to go in here. I'm going to go under StatCrunch, and I have my assisted yoga match pairs, and you can go in. It's in our data group, so you can look at it. I'm going to go to graph. I'm going to select histogram, and we'll choose score before and score after. Okay, and we'll group them by treatment. Okay, frequency distributions. Let's look at the medians and the means. All right, and we need to choose a start at 0. And actually, in this case, because Bartle scores only range between like 0 and 8, we can also use a value of 1. Okay. Y-axis label will be Bartle score. Y-axis label is going to be frequency. And so this is the frequency of Bartle score by treatment. All right, so now we've got 6 of them, and it makes sense because we've got before and afters for each group. So this is the treatment is assisted yoga, and here's its Bartle score, and that looks pretty normal, right? If we look at that, that actually looks very normal, all right? And so that actually, hey, that one works. Next one, well, that one looks kind of skewed left, but it's not terribly skewed, all right? And our mean and our median are kind of at the same place, so that also looks kind of normal, all right? It's not a huge deviation. That one, this one's treatment walking in our Bartle score. That one looks very normal, right? Very symmetric. It's got a single mode. Looks pretty good. Next up, after assisted yoga. Okay. And here we go. We've got that one looks kind of normal. It's a little skewed. Not great, but that's okay. This one, that looks off. It doesn't look incredibly normal. And this one here, that one also doesn't look incredibly normal. So our after treatments actually kind of weirdly don't look as normal as our before treatments. Okay? So I wouldn't want to really trust that too much, even though there's not a huge difference. Now, here's the thing though. If I go in here to my data set, my data set's actually a data set of like, looks like 99 individuals. I have 99 individuals in my groups. And so consequently, if I look, n is greater than or equal to 40. So I have more individuals in my pre and post. So actually, my assumption for normality seems to be to match that one. Okay. Although I would say in this case, it's not too bad. They are what they call roughly symmetric and unimodal. This couple had some outliers, but it wasn't terrible. Okay. All right. Now, let's take a look and let's talk about how each test is calculated. So inside of this test, we'll take the difference between each of the pairs, And then we're going to average the distance between the pairs. This is what's called the mean difference, and find the standard deviation of the differences. Then we construct a test statistic to compare that to the null hypothesis and find the probability of getting that test statistic on the t-distribution. And then that helps us to determine if we're going to find a result. Okay, so I'm going to go in here and I'm going to kind of show you what that looks like. So we'll go in here, I'm going to click on stat. This one is a t-stat, match pairs is a t-stat, and you'll see it's under what we call paired. So my column 1, my group 1, is going to be, actually, we're going to be my score after, okay? Because take a look down here. Mu d equals mu1 minus mu2. So we want scores after minus scores before, okay? And then my scores before, that's going to be my sample 2. I'll group them by my treatment group, right? Because I want to see, are there differences based upon, whether or not we have no treatment? Do we actually get a difference based upon if we use walking versus not walking? All right, so that actually will be important. And then I want to be that mu d has to be greater than 0, right? Really important. If you select the wrong sample to be the before and the after, that changes, right, what your hypothesis should be, okay? So be very careful that your hypothesis, mu d being greater or less than, matches up with your before and after. In this case, I need to do after minus before should be greater than 0. Finally, I'm going to select a p-value plot, and I'm actually going to click on summary statistics because I want to show this too, and then we can go ahead and compute. Okay. All right. So I go in here. All right. First thing that I notice with my test statistics, I'm going to go in and I'm going to, in fact, copy. All right. Okay, so there's my information. Now I'm going to show you a couple of things here before we go into that too deeply. One of the things that I can do in my options, I'm going to go to edit, is I can in fact save my differences. And so what the differences are, we'll show you in just a second. All right, so there we are. There's our values for that. Okay, and what you can see here is if I look here, my differences are, what they'll be is, so score after minus score before, so that's 1. So that tells me actually that I've got the right relationship. Score after minus score before, that's 0. Then I have one of a negative 1. That means that actually my score after was lower than my score before. Okay, and I look and I do that for every single one of them. I actually find the values, these differences for each and every one of them. Okay, all right, and I can store those in. Now, what I'm going to get then is I get something called the mean difference. All right, so this thing here, these are sample statistics for the scores before and scores after. They don't actually play a role too much inside of our calculations. What play a role, okay, is this thing right here, okay? That, for the assisted yoga, it tells me that D bar is going to equal 2.808. So the average difference for our assisted yoga group is going to be a change in the Bartle score of 2.808. That's pretty significant, okay? On the other hand, for the no treatment group, we only have a difference of 0.5, okay? So this is, we'll call this yoga D bar Y. D bar for no treatment, N, is going to equal 0.5. And D bar of W is going to equal 0.9. Okay, so that's my walking group is going to end up being 0.9. Now what this tells me then is that, well, the assisted yoga group actually has a much larger difference, right? In terms of it, we actually got a change of 2.808 in terms of its average difference from before to after. And so that's actually a pretty significant grouping, okay? That's a pretty significant gain. On the other hand, the walking group, just by doing exercise, they got an improvement of independence by almost 1, which might be pretty good, so it's not nothing, but it's not 2.808, okay? And the group that did nothing, their score was 0.5, and this is what's due to just simply maturation, right? Because they did nothing, and so their change due to maturation is just the 0.5, okay? So, consequently, all right, what we see here, one of the ways that I could look at this, and I could say, you know what? That's a pretty significant difference for the assisted yoga. It looks like it's making a difference. Instead, in fact, and we'll talk about this in just a moment, the T-stat for assisted yoga is way bigger than the one for walking, and certainly it's 4 times bigger than the one for no treatment, okay? And my p-value for assisted yoga and for walking, they're also significant. Actually, it turns out no treatment is also significant, okay? So what it tells me is there's a lot of evidence here that suggests that assisted yoga is in fact better than any kind of activity, walking, and certainly much better than no treatment, okay? Even though all 3 of them show a statistically significant difference. Okay. Now, this thing here, this is just calculating our test statistic. All right, and what we did, say for example, for assisted yoga, if you want to check it yourself, is we had T was equal to 2.808 minus 0 over, and we had a standard deviation, a standard error rather, which is 0.3227, or 0.3228, divided by 0.3228, okay? And that ends up equaling, right, approximately, what do we have, 8.4, right? So that's how we find it. We take the mean difference that we got from the sample, right, that's D bar, okay, minus mu D, this should be D bar, mu D, okay, and then we took it divided by the standard error, which is this value, all right? Then we saw, right, that we got, that ended up giving me a p-value, p less than 0.0001, okay? So what does that tell me? Well, remember that alpha was equal to 0.05, so p is less than alpha, so reject the null hypothesis. And what was the null hypothesis? The null hypothesis was that there was no difference. So the null hypothesis was no difference between the two. Okay? All right. Now what we do is we're going to end up putting this onto that t distribution that we talked about in class. Okay? So it requires us to determine our degrees of freedom, which in this case might be n-1. Okay? Calculate our p-value, right? Okay, so that's p, like I said before, p equal to, or p was less than 0.0001, right? And let's take a look now then at our printout. All right. When we look at our, here's the one that has our assisted yoga treatment. So in this case, we could see how far away the assisted yoga treatment is away from the mean. Okay. This mean 0 over here is no difference. And this one's significantly, it's very large difference. When we go over to the no treatment group, you can see that it's much less of a difference. Okay. And in fact, we have that p-value of 0.0266, which is still significant. Oh, wait, it's not. Right? Our alpha was 0.01. The no treatment is not significant. Okay, it's not significant because alpha was 0.01. Making those comparisons, that says, hey, no treatment does not give us a significant difference. And then we see with walking, we do have a significant difference, but not as significant because our T-stat is not as big as it is for the assisted yoga. Okay. So go in, we utilize our stat crunch. We've got so we reject the null hypothesis. All right. And what does that tell me? All right. That tells me that, in fact, that I can reject the null hypothesis. Okay. Now, let's talk a little bit about something else. You know what? I'm going to talk about this in a different video called the Wilcoxon sign test. All right. And we'll do that a little bit later. Okay. So we got for our assisted yoga, we did have a big enough distribution. Okay. We calculated our p-value of p less than 0.0001. Right. We got our assessment. Right. And we assessed our conclusion. And so there is sufficient evidence to reject the hypothesis that assisted yoga has no effect upon independence. So remember, that's our null hypothesis. And our alternative, which we're going to add in here, is there is sufficient evidence to support the conclusion that assisted yoga improves independence. So there it is. We went in, we said, okay, you know what? I've got a matched pairs test. I've got a pre and post that I want to actually make some determinations based upon. So I'm going to use the information that I have. All right, in order to do a matched pairs test, here's my data. I'm going to run matched pairs. I get a t-score, and I'm going to compare that t-score against 0, right? 0 being no difference. And then what I get is I get a p-value and my test statistic. And so if p is less than alpha, we reject the null hypothesis, and that gives me that there is sufficient evidence to reject the hypothesis that assisted yoga has no effect upon independence. And that concludes our mini lesson on the matched pairs.